All right, so here's what's going to happen. We're going to make up an RSA crypto system with a certain number of bits, by which I mean n has that many bits. So I made a little little gadget that lets you type in a number of bits. Let's try something really small first, like 6. What, 2-bit crypto system? Okay, maybe it might be +1 or something. It's roughly 2 bits. So what it does is it will compute the public key for the crypto system, and the private key, in fact, the whole key gets stored in a variable called RSA, which doesn't get printed out. Okay? So first let's decide on how many bits we want to be throwing around. And by the way, in practice, people can easily break 512-bit RSA encryption. So that is a fact. And people have broken somewhat bigger crypto systems by factoring the relevant integers. So it's kind of surprising how big, but like if we try 512, that size right there, so see what E and N are? This is something that with sufficient dedication, it might take a month, that could be cracked right there. That integer could be factored. Let's see, I think the record's somewhere around 760 right now. And it used to be that RSA, the company, had a challenge where they would award a prize for breaking various RSA moduli. But then people kept breaking them, so they stopped awarding the prizes. Which I don't know if that was good for their business. Okay, so let's see. How many bits do we want to use? What? 34. You want 1,034. Okay, you want to go somewhat big? 1034, not 24, but 34? Just making sure. Okay, 1024. Okay, this is actually a pretty common one that people would use in practice. Any other suggestions? Do you want to go really big, go at like 8192? Or do you think this is way too big and annoying? What do you want to do? We have one vote for 1024. Ooh, he wants 2048. Bruce Schneier would say you should use at least 4196. But let's go, okay, we'll just do 2048 as it barely fits on the screen. So we'll use exactly this one. If I click on the full page thing, and now it just fits on the screen. Okay, so there is our public key. So behind the scenes, the code, which I'll show you now, which is hidden by double clicking, I can show you the code. Here's what it did. It computed the next probable prime after a b-bit number that was randomly chosen, and then again it computed the next probable prime after a b-bit number that was randomly chosen. I'm using next probable prime instead of next prime, because if I use next prime it would take a very long time. There is an algorithm in Sage that will deterministically decide, actually non-deterministically but correctly with proof, decide whether or not a number is prime, but it takes quite a while. Still polynomial time, but it takes quite a while. Probable prime, though, is extremely fast and highly likely to be right. Okay, so it computes these two primes, multiplies them together, and then it keeps trying to find an E randomly that is invertible mod phi of n, and when it eventually finds it, it breaks out of this loop and it stores the information. Okay, so that's what this code does. All right, now back to our example. Here it is, and it's been stored in a global variable called RSA. So I'm going to take this big thing, and I'm going to save it. And just to check, there's the encryption number E, and then here's the modulus N, which we cannot easily factor. And I'm not showing you the decryption number D. And so now my confederate in the audience, what's your name again? Matt is going to send me a message. The information he needs is E and N in order to construct a message to send me. So you could encrypt maybe a number, you could encrypt a number like 480, course number, using this. And the encrypted version of this should be like a huge looking number. And then I should be able to raise it to the power of D and get back 480, okay? So I don't know if you're looking at this worksheet right now.
I am.
Okay. It's kind of cheating because you could actually just compute the D, but let's not do that. So what you should do is paste into the chat an encrypted message. So what does he have to do in order to do that? I guess you could actually do it right here. So what he needs to do is compute modulo n something. He needs to take 480 modulo n and raise it to the power of e. So I don't know, do you have a worksheet open where you're going to try to do this and copy paste? Okay. Is it in your own project or in this project?
Can I edit this project?
Yes.
Okay.
Because I can open your worksheet so everyone can see it up here.
I can do it in this project.
Okay.
In this worksheet.
Yeah, maybe you could just do it right here in the worksheet where it says a live demo. So if you open this and start typing, your character should appear here. Yep, good.
Yeah. Okay,
Right,
so what do I do?
So what does he do? Help him.
480 to the E.
Right. 480 to the E. But if he does that, that's going to be bad.
Mod n.
Yeah, mod n. So make sure you
What's the notation for mod n?
help him.
You want to use that sage notation because then it will use all the sage stuff specifically. So
Do something like that. Like mod.
some operators are overloaded for that.
Yep. And by the way, I haven't set n yet, so let me go back up and tell you. To get n, you have to do this notation right here. My RSA square brackets n. Yeah, and then quotes n. And so if you were doing this in a different worksheet, what you would have done is sent, like in an email, you could send your public key by sending that pair of integers. And then the person would just copy and paste this pair of integers in, and then they would be doing this, okay? So now you're going to raise this to some power, and the power, the E, is also stored in this dictionary my underscore RSA. So that looks good. Caret, and then my underscore RSA. And what do you expect to see when he hits Shift Enter? A big number, right? Okay, do it. Okay, that's the encrypted message right there. And of course, if he does it again, he's going to get the same answer because it's just arithmetic. So if you want it, what might you do if you wanted to make it so that every time you encrypt 480, you get something different out, just to throw off the enemy? Any ideas?
You just add some text. You could add some like waste text to 480.
Yeah, you could always encrypt your message as your number plus, I don't know, 10 to the power of 50 times something. And then when you decrypt it, you just get rid of the 10 to the 50 part. So you just add something random like that. Or just, yeah, I mean, that's what you'd want to do, something like that. Because you have to be able to tell, yeah, it lowers the bandwidth of your channel because you can send less information each time, but you have to add this extra randomness in. It's called salt, and it's a good idea. Okay, so there's this number. Now I'm going to take it. I received it in an email or something, and I'll go mod that big number, comma, I can't remember what it is, my underscore RSA n, and I'm going to raise it to my underscore RSA d, my decryption key. And let's check if Euler's theorem really works for such big numbers. Boom, I get back 480. There it is. So RSA worked. Good. Actually, I just thought of something possibly amusing to show you. Let's take this big number, and in a terminal, there's this program called GP which Sage uses, and it has a factor command. I know you probably can't see that, but I'll just move the window up temporarily. It has a factor command with a verbosity option. So we can paste in this big number and then put a 4 there, I think. And it'll sit there. What just happened? Did I put the wrong number in? Seems to say it's prime. Doesn't make any sense. Oh, I didn't put in n, I just put in, I guess, the encrypted value. It just started with 8, so I was thrown off. No, wait, I did put... Maybe the 4 means do trial division. Let me look at the help for factor. I just know how to use this from Sage. Why am I not just using this from Sage? Factor the number, and I think if I say verbose equals 4. Yeah. So what this does is it will use a suite of factor, or it'll be even funner if I use verbose equals 8. What it does is it will try to factor the number using a whole bunch of different algorithms, and it will very verbosely tell you what it's doing along the way. Okay, so this is doing all kinds of things like checking if it's an odd power, trying something called the polar Brent row factorization method, trying something that involves a quadratic polynomial 32 times, etc., etc. So it'll just sit there trying to crack the number. It will not succeed, probably, but it'll sit here and try as long as you just leave it running. And it's nice because you could see it as it's trying, and you can see what techniques it's using. This is using now the elliptic curve method, which is an approach to factoring that I just mentioned. So it's going through these various algorithms and trying them out. All right, so back to this. I'll just leave it running, and we can check to see what happened later. All right, what might you want to do next? Another thing we could do, we just did the send a message thing. Remember, there's a couple of things we can try. We have time. One we could do is we could actually, let's see, if I show you, let's try this phi of n gives you back a factorization of n business, okay? So we actually secretly know the factorization of, no, actually I don't know the factorization of n. I didn't save that. Crap. But I do know d. So question, if you know d and e, is there any way to get phi of n? Any ideas? Because I do know d. My underscore RSA d is that. But I'm pretty sure I completely forgot to save p and q. So let's see. Let me check. Yep, I completely lost p and q here. Forever. But goal. Given even knowing the private key, can we factor n? Any ideas? Say that louder. I can't hear. I still can't hear you. Can you factor ed minus 1? Probably, let's see. That seems like the only hope. So he points out that e times d minus 1 is divisible by phi of n, because e times d is congruent to 1 mod phi of n. Factoring it might be kind of hard because it's a really, really big number. On the other hand, maybe it is just phi of n. Because think about it. Well, it's not going to be that much bigger than phi of n. Maybe it's twice as big. I don't know. I'm annoyed. I want phi of n. Well, at least let's just see what it is. T is e. If you let t be this product, then t, which is going to be a very big number, is divisible by 5. What just happened? Oh, these are numbers modulo n, so. Actually, wait. E and D, why is that 0?
Maybe you can mod 5 then.
Yeah, maybe.
Because it should be 0 then.
Integer ring. Maybe D is modulo. Aha! Hey. That looks like n though.
That's not it.
That's not n. Maybe that's phi of n. Could that be phi of n? That is actually... Nope.
No, it's not.
No, it's not n.
It looks like it.
It looks like it's a lot like n, but at the very bottom it isn't. Okay, so it looks like, it turns out, when I computed d in the code, I computed it as the multiplicative inverse of e modulo phi of n. And I just recorded that, and d remembered its parent, that is, that it's a number modulo phi of n. So we actually have phi of n. Yes. Okay, so this number right here, which I think I can get it as the modulus here, that'll be phi n. Yep. Okay, modulus square bracket 0. There it is. That number is phi of n. So now we have n and phi of n. And I'll just let n be my underscore RSA n. Okay, so we now have n and phi of n. So now, let's see if we can figure out what the factorization is more quickly than that other factorization that's currently running. All right, so we have our code, or we have our numbers, They're just enormous looking numbers, but we also have our theoretical understanding of what we want to do. So combining these things, we should be in good shape. So what happened? Let's look at the board again. So on the board, we realized that we could compute p plus q by computing n plus 1 minus 5n. Okay? So let's just do it. P plus q, scroll this up. P plus q, you see it at the very top, is, P plus q is what? It's n plus 1 plus, n plus 1 minus phi n. Okay? And p times q, really spell it out, is n. Okay, so now we just need to make the polynomial, the quadratic polynomial that has these p and q as roots. So let's let f be the quadratic polynomial x squared minus p plus q times x plus p times q. Okay, it's going to be a quadratic polynomial. Boom, we've now hopefully made that polynomial. I don't see why this should take a long time, but it is. Oh, it's done. Now we can print it out. It's just going to be some huge looking quadratic polynomial. There it is. It's pretty big. And now we just need the roots of this massive polynomial that's taking up the entire screen, which we should be able to compute with ease using the roots command, f.roots. See what it does. It computed the roots symbolically in terms of the quadratic formula, which isn't helping at all. So it used the quadratic formula and gave us back square root of something, but that's not so useful. That's a little weird. It should have just given us back integers, given that the roots are integers. So I'm a little puzzled by that. But maybe for efficiency reasons, it doesn't try to simplify the square root when it's really big. But you can do things like, we can say RR, and then that will give us the roots in the real field, numerically. Real field is not a valid variable. Okay, maybe it doesn't. I thought that's how roots worked. Oh, we have to give the variable and then the ring separately. Okay, so we want the roots of this viewed as a polynomial in x, and we want the ring to be RR. Okay, there they are, but unfortunately, that can't possibly be right. One of them is minus 1. Did I mess up the algebra? It's clearly not the case that minus 1 is a root of f, is it? Could be some weird rounding errors. Let's see. Let me try working to much larger precision. Nope. Minus 1. What the hell? That's very weird. Huh. I'm really annoyed. Okay, so B is that. Okay, I'm asking for the roots to 50,000 bits of precision and printing it out. That's probably stupid. Okay, we'll see how it goes. It still thinks that minus 1. Well, there's a lot of numbers there. But annoyingly, yeah, okay, so that's really annoying. It's not giving, so we're not just formally easily getting the roots, and we're out of time. Let's check if this factorization succeeded. Of course not. It's still working away. It's going to try very hard for a long time and totally fail. Whoops, sorry. Yeah, I must have missed a sign or something, because I don't know.
I think your B is 0.
Ooh, let me go back to where I defined f. Ah, maybe it's, no, p times q. That sign's right. Maybe the sign's wrong here. Maybe that's not p plus q, but
I think it's 0.
what is 0?
P plus Q.
P plus q is 0.
Must be a misspelling.
That's possible. I could have chosen my 2 primes randomly to be the same, or I could have. I don't see any. I don't see any problems. I don't know. I'll have to get to the bottom of it later. That is weird. But you must be convinced that correctly implemented, this has to work to give you P and Q. And of course, this is exactly what always happens when you crack something. You have to have some theory that tells you what should work, and then you try it, and it doesn't work because you screwed up somewhere in implementing it. But that's why the theory is extraordinarily helpful, because you'll persist in the right direction rather than the wrong direction, like working randomly. So, very weird. Finding with multiplicities. God.
So the limit outputs of an alpha was positive. Should
Yeah.
be negative.
But it's x minus alpha times x minus beta, so it should be alpha times. Oh, you mean when I actually wrote down the polynomial, it actually was just negative.
It gave.
Well, that's positive.
No, I mean earlier when you printed f, it
Mhm.
produced something with linear terms positive. It gave minus positive. So that in front of the x squared is plus 8.58.
Yeah.
Which I think should be negative to get.
Oh, that's true. That definitely has to be negative. So that minus there should be a plus. So the algebra must be wrong right here. N plus 1 minus phi of n. Or maybe my
Maybe-
phi of n.
maybe
I bet
it's
my sine
capital.
of phi of n is wrong. I bet you phi of n is negative. Or something like that. Nope. But you're right. Let's just try the other sign and see what happens. Plus. Okay, now at least that's. That must be a number modulo something rather than an integer. I bet you that's the problem. So this needs to be coerced up to the integers. One or the other. Yeah, now it's negative. Now it's bigger. And now let's see what the roots are. There aren't any roots. Okay. There have to be roots though. It's ridiculous. It must have roots. Just making sure everything is an integer.
Minus 1. I think that something was being computed modulo n. So maybe one of them is cancelling out the other.
Yeah. Yeah. But since I put ZZ around everything now, nothing's being computed mod. Anything funny? P plus Q. Now I'm confused. What this does is it forces it to construct a polynomial ring over the integers. So it's a little more precise. The size of this number is about right. Why doesn't this work? Does it factor? P times Q is N. Has to work. Maybe I set N incorrectly? Nope. N's definitely right. 5N. The sign of this could be wrong, actually. Actually, the sign is wrong. This is wrong. It's right here. It should be minus that. So when I say modulus, what it does is it gives a linear polynomial, which is x minus phi of n. So that's what's wrong. Well, let's see. In any case, this is where it's wrong. It's right here. So let's just fix it correctly. So that's x plus something. That's really x minus phi of n, I guess. What is this? Univariate polynomial ring over the ring of integers modulo that. Okay. Let me just look up at the top how the thing was made. So I made mod e comma 5n. That's so annoying. You know, instead of modulus, I think there's another method that would just give like the number that's the integer you're working modulo. So, I mean, we could also just copy and paste because it's the ring of integers modulo that. So that number right there has to be phi n. Just as an integer. Okay, so then that should give everything. No. There it is. That's P and Q. I factored it. So I can now do roots. So basically I was off by a sign because of how I hackily got at phi of n. But here are P and Q. So if I do V equals this, then P equals V0, 0, and Q equals V1, 0. And now if you do P times Q equals N, it works. Okay, so for the screencasters at home, now it works. Ah.